Carlo Baldassi on entropic algorithms and white flat minima. Carlo is sharing his screen that we are seeing. Yes. Good.
Can you? Okay. Of course, full screen mode doesn't seem to be working. Okay, so let me just try to backup plan. Maybe this way.
Oh, that's okay.
See, this looks okay. Does this still look okay?
Carlo,
yeah,
maybe
if
full
you make
screen
it
works.
maybe slightly bigger, the window.
Yeah.
This is full
this
screen.
Way?
Now we see full screen. Yeah, we see full screen and we see the slides changing.
Great.
Okay, Carlo.
Great.
The floor is yours.
Thank you. I'm going to present the latest in a line of works that we've been doing in our group. And the paper is this one, just uploaded on archive. And as you can see, it's very much a collaborative effort. And it's about basically wide flat minima neural networks and how entropic, what we call entropic algorithms, can find them and their properties. So I'm sorry. Sorry, because this is an older version of the presentation that I had. I'm very sorry about this. I have to recreate the PDF. I wasn't expecting this. There should be done, hopefully. There. Okay. Yes. So I had an outline. Anyway, so I'm going to do a little bit of introduction, of course, where presenting the general problem and summarizing our past results that we build up on for new theoretical results on Gaussian mixtures and some new numerical results on deep neural networks. So the general theme, general setting is that of analyzing the complex lost landscapes in neural networks. So, of course, we know that neural networks, especially deep neural networks, are very highly non-linear functions which have very non-convex landscapes with many local and global minima, at least in principle. And yet, despite this, they seem to perform well in terms of generalization, to be rather easy to train in some sense, and so on. So this is sort of a puzzle that many people, including us, have been investigating in the latest year when the success of these machines has become apparent. And one among the many results that are available that I want to mention is that there seems empirically in numerical studies, consistently there seems to be some sort of flat, non-convex bottom, where by bottom I mean basically global minimizer. So which is accessible and connected. Something like shown in this heat map here, an entire region of global minimizers that are all connected. And this is just one example of a line connecting 2 points, but there seems to be a rather complicated geometrical structure there somewhere, and also which is sort of easily accessible, provided one employs a few, let's say, the usual, let me call it the bag of tricks that are employed in machine learning, in modern machine learning with deep neural networks. So the lost landscape depends obviously on the data, but that's not something that one can choose generally. But in terms of the choices that one can make, the loss function, the loss landscape, depends both on architectural choices and the algorithmic training choices. So in terms of the architectural choices, one can choose loss activation functions, whether to use batch normalization or skip connections. For example, here we see a striking difference between a landscape in which no skip connections are used and one where they are. Of course, this is a projection because two dimension, but the idea is rather clear. So these all influence the roughness and the larger scale structure. And also in terms of algorithmic choices, one might use dropout and so on, and decide the size of the batch in stochastic gradient descent, choose which loss function to use, and so on. And this is all because these training choices, actually, they affect whether we find global minimizers or not, but even when finding different global minimizers in the loss function, they might still have different characteristics, because in the end, what we actually want these networks to do is generalize well, obviously. So the question here, the main question that we address or study, is how to tell apart good minima, which means good at generalizing, from the bad ones or worse ones. And of course, a related question is then, if we can characterize good minima, then how can we find them algorithmically in an efficient way? But the basic point is how to tell apart good minima. And well, there's a mounting body of evidence, so including some of our works, which shows that flatness of the minimizer is a good measure, is a good predictor of generalization properties. There's a correlation there. So basically, it means flatter minima tend to generalize better. There's no actual rigorous connection there, but that seems to be the case. Let's say there's at least some intuition, it's supported by intuition, some theoretical calculation, empirical evidence, and so forth. So what we did, we started from a statistical physics angle in our case and defined what we call the local entropy loss as a way to characterize this flatness. And so the formula is here. One thing to point out immediately is that this local entropy for a given configuration is defined in terms of a different loss. So it's some sort of an auxiliary loss in a sense. So one chooses a loss first and then computes the local entropy. The interpretation of this formula can be summarized this way. Apart from the minus sign and the logarithm, which are not essential, what this does is to measure a volume of configurations called W prime of the network, which are below a certain loss. This is controlled by this parameter. So we are going generally to use a large value of this inverse temperature beta, such that we keep this small, but also we want to keep the volume within a certain distance from the reference. So given a reference W, we explore the surroundings within a certain distance, which is controlled by this term and this parameter gamma in particular. So, of course, the larger this volume, the flatter the landscape in a sense. And here we have a cartoon of what happens in a one-dimensional example when we start from an original loss, L, let's say, which is the gray line. It's very rugged. It has some isolated global minima, some wider global minima, some lots of local minima, and so on. And we compute the local entropy loss with a small gamma, which means large distances, which means it's basically a coarse-grained smoothing of the landscape. And we see that indeed we get a much smoother function, the global minimum of which is close to the region that we're interested in of larger global global minima. And then if we can get here algorithmically, then we can start looking at more finer features, so increasing gamma, and the local entropy landscape becomes something like this, and going further becomes something like this. So if we manage to follow this minimum, we end up basically in the middle of the desired region of wider minima. Okay, so this is the idea. One nice thing about this function is that it can be used in statistical physics with a statistical physics approach. And that's precisely what we did, of course, using replica theory results. There are all sorts of technicalities here, and the results are non-rigorous, but they can be checked a posteriori with numerical simulations. And we did the theoretical analysis on shallow neural network models, so 1 or 2 layer networks with continuous and discrete weights, lots of different variants. We analyzed lots of different models, and in order to summarize the results, what we find is very consistently, is that these neural network models all seem to have accessible flat or dense, whatever you want to call them, regions as a structural property. And by this, I mean that these sort of regions they are present even when the input data is random IAD, and even when there's actually nothing told to generalize. So this is rather surprising because one would think that the data that one is trying to learn is crucial for the presence of, let's say, Y's plus minima of minimizers. Yet it seems from this analysis that this is not the case. The data is obviously important, but even in absence, so the structure in the data is obviously important, but even in absence of any structure, still some sort of region like the one that I was mentioning here seems to be present. So this is the first observation that we found in all models. And the other is that when there's something to generalize, then lower local entropy loss means better generalization performance, essentially. So again, flatter minima generalize better. That's the general takeaway. Other extensions of this this kind of analysis that we did was comparing, let's say, traditional 80s, 1980s style activation functions like step functions and tanh with what become popular in recent years, which are rectified linear unit activations. And we saw again, even these simplified models, that not only these different activations still have these regions, but they even have wider and flatter minima. So in this sense, one might think, one might justify the use of this sort of activation as by saying that they are better than the others because they create flatter regions in the landscape. Something similar is also true for cross entropy, for example, when compared to some other more classical loss function, which is the mean square error. There's a caveat here that will become, say, more relevant in a moment, so I might mention it right away. There's a discrepancy when we use the loss and we speak of the loss landscape. Generally, what we speak about is the loss that is used for training, because normally we use SGD for training and we require a differentiable loss, whereas when we actually want to use the network, we use for testing purposes, so on unseen data and for ascertaining how well it behaves, we use the classification error instead, which is typically performed with some argmax function or step function or some such. And that's not differentiable, but this is what we actually do care about, the error. And so the loss is just an auxiliary, let's say, a training choice rather than an architectural choice in this sense. And what we found is that, so I might also mention this, that when we speak of the local entropy and we do the theoretical computations, all the works that we did so far were using the error here, because in the local entropy definition, we don't need a smooth differentiable function, so we just plugged the error function here. And what we found is that using the cross entropy loss and optimizing that, for example, with SGD, has as a result to get to configurations that have a better local entropy computed in with the classification space. So this is kind of a subtle distinction, but it's kind of getting into play in a second, because now we are trying to move away from this in order to bridge the gap with between, say, the theoretical models that we've had studied so far and what people actually do in practice. So we have some additional theoretical results on Gaussian mixtures, and we moved away from our previous theoretical results in two senses. First, we managed to study theoretically non-IID random data. We did have results on these kind of things, but only numerical ones, not theoretical ones. And also, we are defining the local entropy now, not on the error loss, but on a differentiable loss, because that's what can be done, let's say, in practice so far. So we wanted to analyze this scenario because we want to bridge the gap with what we do then on deep networks. So Gaussian mixtures, they've been mentioned just in the last talk. I'm presenting an a fully simplified version of this. It's a classical, important, popular model in high-dimensional inference, statistical inference, the model is defined like this. There are 2 points called V star and minus V star. These are the centers from which data is generated. One is associated to labels +1, one is associated to labels -1. The data is generated, the data points are generated according to a Gaussian distribution with a large variance such that the 2 clouds of points have a quite large overlap, and basically perfect classification is impossible, perfect generalization is impossible in this model. So this is in 2 dimension, the picture, but of course we're working in very high dimensionality. As a classifier, we take the simplest possible things, so a perceptron, meaning something with no hidden units whatsoever, that predicts, for each input, predicts a label by just computing the sign of the scalar product. So of course we want to find the W's that give us the best possible generalization performance. And this model has some nice features, some not so nice ones. The nice ones are that it's rather simple. The data is sort of structured and also hard to classify because of this overlap. It can be analyzed theoretically very thoroughly, and the optimal W can actually be computed rather easily. But one can ask, what if instead of computing the optimal W, say from the theory directly, we try to study what happens when we employ the techniques that are normally used in deep learning. And this is basically what was done in this paper by Mignacco et al., where what they did was considering the mean square error or other losses, but differentiable losses, and see where we end up, essentially. And this case is shown in this picture here. This is the number of input data. This is generalization error. And you can see that the top line is the one in which one naively just optimizes the mean square error. And one sees some features that are also present in neural networks. And in this particular regime, which is the one that we are most interested in, which is the over-parameterization regime, where there are more parameters than data, essentially, one can see that the error is rather large, and there's a large gap from there to the actual optimum, which is below here, the base optimum. However, it was shown in this paper that one can achieve this base optimal estimator by adding an L2 regularization, so controlling the norm, essentially. And in this particular case, one needs to get to infinite regularization, lambda, in order to get the bias optimal. But there's a monotonic improvement. Now, this is all fine and interesting. There's a slight, there's something strange here, at least on the surface level, because one can observe that the generalization error depends on this function here, the sign, which is not differentiable, and in particular does not depend on the norm at all. What depends on the norm is the mean square error, which is an auxiliary function, the loss that we use just for the training. But then one controls the norm of something of which we don't, the norm of which we don't really care about. So this is kind of strange in a sense, and possibly not very easy to generalize. I should mention that this phenomenon that of say norm invariance is also present in most deep neural network models, which use ReLU regularization and perform an argmax at the end. So this carries over this sort of issue that controlling the norm is not directly relevant for the classification performance, and yet seems to be some sort of an effective strategy. So what we did was instead wondering whether we can rework this, reanalyze this problem using the local entropy framework, which is what we did. We had 2 stages of this kind of analysis. The first one is to take these sort of solutions, the one that we now generalize better, and compute their local entropy, so compute their flatness, essentially. And this is what we did. The function that we have defined here is still very similar to the previous one. The difference is just that the constraints on the, well, first of all, the error is used instead of the loss. Then these are step functions. So the constraint on the training error is given in terms of a hard constraint and also that of the distance. And it's also renormalized such that the maximum of this function is 0. But in a nutshell, given any w, we can compute this function for different d. And this is bounded above by 0. And the higher, the better. And the higher, the flatter, in a sense. And well, the cures are here. We see that when we look at solutions found with increasing regularization, which means solutions that generalize better and better, and then we compute this local entropy, we find that those that generalize better are indeed flatter in this, with using this criterion. And the other part of the analysis is, well, what if we instead start from the local entropy and try to optimize that directly? So optimize for W in a sense, for given D, for example, something like that, without regularization in a sense. So this is what we did. We also changed the function to use the loss now. As I was saying, we are trying to move away. We are trying to move to a case where we can use the differentiable loss here in the definition of the local entropy. So this is what we did. So we studied what happens when one tries to optimize local entropy at a given D computed over the mean square error landscape instead of the error. And the reason for doing that is because this can be implemented algorithmically. I'll speak about the algorithm later, so I'm not giving too much detail right now. But one thing to note about this problem is that this is convex, so it's quite different in this respect from what happens in deep neural networks. And in this particular case, the optimal distance d to use here is basically as large as possible because of this convexity. And as a result, in any case, is that the dependence on the norm disappears, and we do recover the base optimal configurations basically independent of the norm, and this is confirmed by simulation. And well, basically the differences between the top curve here, where we see the usual naive, non-regularized, non-replicated, the usual naive optimization of the mean square error, where increasing the norms worsens the generalization error, and we see this overfit, to our version where by increasing this D and computing the local entropy, we progressively go towards the base optimal regardless of the norm, essentially. So these are the theoretical results, which again show, even in this very peculiar case compared to the ones that we studied before, that local entropy is some sort of good predictor of generalization performance and effective algorithmically. So the last part, I'm going to talk about numerical results that we have on deep networks. So now we're starting to consider something very, very much larger than what we had before, which were 1 or 2 layer networks. Now we have 110 layer networks or something. And I'm going to speak about what we call entropic algorithms, meaning algorithms that directly are designed to target directly the local entropy loss. So there are 2 such algorithms that we have. One is called entropy FGD. It's defined this way. This is a formula that I showed before of the local entropy. Something that I haven't mentioned is that the local entropy is rather hard to compute. We can compute it with some difficulty, but we can compute it in the theoretical computations. But in practice, on an actual network, especially a realistic one, this is hard to quantify because of this integral, essentially. On the other hand, if we compute the gradient of that, what it turns out to be is basically an expectation of this quantity denoted by this angle bracket. And this expectation it's easier to estimate by some Monte Carlo technique. And it can essentially be approximated sufficiently well by using stochastic gradient Langevin dynamics, for example, which is also quick enough, let's say, algorithmically, it's also efficient enough. And so this gives rise to an algorithm which is called entropy FGD. Another one is called replicated FGD. Now, this comes from starting from a Gibbs distribution and doing some algebraic manipulations. I'm not going to get too much into the details of this. We end up with a different loss function, but it's a loss function defined not on a single model, but on a replicated system of models. We see here a cartoon in which, say, there's one replica representing a whole deep neural network, and this is replicated, and they're all interacting with yet another replica. So looking at the loss, the structure is that each replica called WA just optimizes its own loss, and then there's an interaction term where each replica is attracted to the barycenter. W bar is the barycenter of all the replicas. And why this works is described here very roughly. Basically, if one could do Gibbs sampling of this replicated loss, it would be basically essentially equivalent to a system in which the barycenter W bar explore the local entropic landscape. This is purely for algebraic reasons. So here in the cartoons, you see that there's this center with the replicas that interact with those. And the idea is that this replicated system is able to, because it uses the local entropy, which has this moving effect, is able to jump over local minima, isolated local minima, and get to better, flatter regions, essentially, very, very roughly speaking. Now, Gibbs sampling, of course, is expensive. So instead of Gibbs sampling, one can try and do stochastic gradient descent and just use the noise from stochastic gradient descent, although this is very far from perfect. And this would mean that the barycenter W bar just approximately explore the local entropic landscape, but it's a viable strategy. And it does work in practice rather well. Of course, it's possible, slightly improvable, but it's simple at least. So these are the two algorithms. They are quite simple. So for example, this replicated SGD is just really a few lines of code of modification with respect to a normal algorithm. One can go through it very, very quickly just by looking at it. At each step, one can just compute the barycenter of the replicas. And then for each replica independently, one samples mini batches, computes the usual gradient. So this is just a standard algorithm. One can change this gradient update to using Adam or whatever other optimizer is desirable. The only difference here is that every once in a while, so every, let's say, k steps, then the individual replica gets pushed towards the barycenter. So there's this attraction term, and this is sufficient to drive the whole system, the system as a whole, towards dense, larger, wider regions. And entropy SGD also only has the usual gradient descent and then some few cheap, let's say, other updates. This capital L here is the Langevin dynamics parameter, so how much sampling we do. Generally, we don't need much sampling, and generally, we don't need too many replicas, as I'm going to say. And so finally, we did the experiment on this. We experimented with some state-of-the-art networks on realistic data, image data. These are all convolutional networks. And as a baseline, we just considered the models as specified in the papers where they were presented. So just from the literature, we took the parameter, the parameter that specified the model and trained them, and this is our baseline. And then we try to apply replicated SGD and entropy SGD, so these entropic algorithms, with the criteria that we wanted no additional fine-tuning with respect to the baseline, at least for the usual hyperparameters. So something like the learning rate and such. So no more fine-tuning there. We just fine-tuned basically the parameter gamma, which appears, you see the parameter gamma, which appears both here. There's also this K here. And the other parameters that appear here in entropy SGD, this one has a few more. So those were fine-tuned to an extent, even though we tried to limit that, but not anything else. And also we did a comparison as fixed computational costs. So wanted to check whether these are viable practical alternatives, meaning that, for example, if for replicated SGD we had 3 replicas, then we ran it for 1/3 of the epochs as the baseline, meaning that overall they spend the same amount of computational time, and the same for ESGD. And across the board, we see an improvement, as you can see, in the generalization performance. And then there's also this case in which we have basically replicated SGD, but assuming that we can run it in parallel, which is quite not hard to do, then one can compare this with the same number of epochs as the baseline, and one can observe even larger improvements. So here, for example, and in general, this one has quite large, and so on. So, by the way, we used only 3 replicas, for example, for RSGD. These are sufficient to change the dynamics of the algorithm. More would be better, but then there are obviously limitations in the computational costs, so it's expensive. So, but this trade-off seems to already provide good performance. Finally, we have performed experiments where we tried to check that our entropic algorithm do indeed find flatter minima, and that the improvement in generalization is not random or by chance, let's say. So, as I said, local entropy is expensive to compute. So in order to do this kind of measures, we used a cheaper flatter measure. Now, this measure here was introduced in this paper, which in this paper, this is by the Google Brain Group. They performed an extensive numerical analysis trying to compare several different measures taken on the loss landscape and checking which one of those are the best predictors for generalization performance across several different neural networks, data sets, and so on. So this is a very wide study, let's say, and they found that flatness measures are the best or among the best. And this is one of the measures. It's basically starting from any configuration W, there's a multiplicative noise where Z is taken from a Gaussian distribution. Sigma is a parameter that tells you the distance. Then one computes the error of the perturbed configuration and the expectation over the noise and compares it to the original one. So varying this parameter sigma, one gets an average profile around the original point of the loss landscape, essentially. Such as those that we see here. So this parameter that tells you how far you're going from the original point, and then the train error difference. So this is not even the loss, this is train error. And this is the profile, the average profile. And what we see is, in our experiments, is basically a confirmation of what we would expect, namely that entropic algorithms do explore flatter regions throughout the training, not just at the end. And so we see here different epochs, for example, and we see that generally all algorithms have a tendency to get to flatter regions. But even at the end, you can see that the two entropic algorithms are flatter than SGD, even with this simplified measure. I should say probably at this point that we do believe that when we say SGD is actually, say, the baseline, and the baseline has been obtained by basically optimizing the architecture and the hyperparameters and all the algorithmic techniques, such as to obtain the best possible generalization performance. So our understanding of this is that even SGD itself is already targeting wide flat regions itself. So it's not like, so gradient descent by its own, for example, would not get to something like this. That's what I'm trying to say. So it's already been optimized, let's say, indirectly through trial and error and employing clever tricks from the machine learning community. But there's still something to be gained by using these other algorithms, at least according to our tests. Okay, so I think this is all I had to say. I had only conclusions and perspective. How much time do I have? Sorry.
We are basically in the discussion time now. So,
okay, so
minus
then
2 minutes.
Okay.
2 minutes in the 10-minute discussion.
Okay, I think I can just speak about these in case there are no questions, and then I think I'll take questions now. Thank you. If there are any, otherwise I may comment further on this.
Yeah, that's a good idea, maybe. Okay, thank you, Carlo. So, do we have questions? Please feel free to step in if you do. If not, I mean, I can start maybe.
Yes.
Before people step in. So I was wondering for the Gaussian mixture example. So you showed us the analysis for the square loss.
Yes.
And I was wondering whether you also looked at the logistic loss, because of your previous results, the logistic loss should find flatter minima. That you were citing that paper, and here logistic loss actually does worse. So I was wondering how that. What's the flatness of the minima it finds?
Okay, so thanks. No, I mean, we did not look at logistic loss. One reason is that this mean square error, yes, as you said, it does worse, and so we focused on the one that does better, in a sense. But also, when I said that this cross entropy, which is basically the same as the logistic loss, it's better, let's say, compared to MSE. That was on neural networks, of course, first of all. So it's on a very much non-convex case. And I should point out that this seemed so this was studied. The comparison in this paper here was optimizing the cross entropy directly and then looking at the local entropy of its result, as opposed to optimizing the local entropy directly. Here, when we studied the MSE, we actually wanted to get to the case where we use the MSE in the definition of the loss. So in the previous study, we compared this function where this was the error with another loss here at this level, let's say, which was the cross entropy. In this case, we wanted to put the mean square error here and compute the local entropy of that. And this is because our aim was to bridge the gap with what we do here, where we actually do need a differentiable loss even in the local entropy definition in both these algorithms, because if you look here, we need to be able to compute this gradient. So I don't have an answer to your question from the theoretical side, basically because we did not do it, but I can tell you that in all these networks, the loss is actually cross entropy. And in fact, this is what we are taking the gradient of. So it seems to work well enough, I would say, but I don't have a precise answer, sorry. So I don't have anything more precise to say.
Okay, do we have other questions?
Does this answer the question at least?
Well, it answers is that you don't know, right? So
well, yeah,
I was just wondering.
Side, not on the theoretical side.
I mean,
on that model,
the right. For me, this is kind of a possible. If there is a chance that this would be a counterexample, that the flatness of the minima the logistic loss finds is good, whereas its generalization error is bad. But so kind of disapproving this DAP would be kind of reassuring for me.
Okay, yeah.
But you haven't done it, so that answers the question.
It shouldn't be too hard to do it. I mean, it's just a matter of plugging a different function in the replica definitions.
It's the same calculation.
Yeah.
There is in the chat. No, question. Florian, do you have a question?
Yes, please.
Okay.
So, okay, that was very interesting. In the beginning, you showed people had apparently plotted the complex loss landscape. And I guess this must be numerically very expensive. But my question is, can one do a numerical experiment where one gets the variance of the original loss landscape, in the sense that you take all your training samples, subdivide them into 10 sets, and then recalculate, and then you could compare against what it means, how it correlates against your entropy loss?
Well, I am not aware of people having done these sort of things, in the sense that I mean, I know that people have been studying numerically this sort of properties of, say, the variance, and also the variance in various directions, and observe the properties about how the stochastic gradient descent is affected, and the level of noise. I mean, because what you're speaking about is the variance when you take batches, essentially, and this affects the noise term in stochastic gradient descent, and it affects it in a non-trivial way. So I am aware of studies that have studied that. I'm not aware of any visualization, honestly. But yeah, sorry, I don't remember the name right now of the people involved in that study. But I can drop it down in the chat if you want, if you're interested later.
Thank you.
So far I don't see other questions, but I have one. I was about your experimental study with the deep network. So I appreciate the fact that you try to match the computational time. So you try to make the comparison fair. At the same time, it kind of worries me, because in all these fancy models, the early stopping is always really important. Like the generalization error depends on the time in a non-intuitive way. So they probably kind of fine-tuned also the early stopping. And then you said that you just match like 2/3 of the time. So that kind of worries me, because wouldn't the early stopping should maybe happen before or after? Can you comment on that?
So basically, we are shooting ourselves in the foot here, in a sense, because yes, this early stopping was fine-tuned to some extent, even though in our experiments, say here, we've seen that by by going slower, we can still improve this baseline. So it was fine-tuned, but it still can still be improved, possibly. In any case, probably it could be even more fine-tuned with these algorithms, but we did not really do that.
Yeah, could that maybe explain why this like 15.5 is actually worse than what the just entropic SGD gets in the first line?
Well, this one,
like in the first line, you get the 15.5 for the combined method, for the parallel, for the
this one here. Well, you mean if you run the baseline for longer?
No. If you run the fourth column for longer.
Well, I mean, in general, we've seen that with these algorithms, if we run them for longer, then we can improve the result. That's true for RSGD. Here you see it, but it's also true for ESGD. That's something that we are just not showing. So we can improve further. It's just that we are trying to improve it with the constraint to not go over the time of the baseline. So yeah, there's still more tuning possible. One other possibility that we are seeing is that if you increase the time, generally you tend to gain more from this entropic algorithm than you would with the baseline. So I mean, the baseline can be improved if you give it more epochs, but then if you also give more epochs to the others, they still improve more yet. So
there is a question by Max.
Hi. Yeah, I'm just wondering if so there is a relationship with, I think, with soft weight sharing. So soft weight sharing is a very old paper by Jeff Hinton, basically. Yeah. So and so I just wonder if you take your loss and you take a variational bound by introducing a variational posterior over W, and you take and then you take basically the outer, the loss function is then a function of your mean, the means that your sort of the hyperparameters, which are the means in your, yeah. And then the inner one is basically an optimization over your posterior distribution. I think you just get back to basically a Bayesian formulation of your problem, a variational Bayesian formulation of the problem with a soft weight sharing prior on it that you also update on the outer loop.
Okay, I'm not sure that if we recover exactly that. There are different interpretations of this. So this replicated SGD, as I mentioned, that's the other interpretation. But this entropy SGD, for example, was shown it can be interpreted as can be interpreted sort of in a way that, as you said, I know, I'm not sure, but what I can tell you is that it was used in a pack-based framework.
Yeah.
But not directly. There was, I mean, it was shown to be optimizing a sort of pack-based bound. But this is the important point, even in this study, is that this sort of regularization is point dependent in a sense. So because
if you go to this one, so if you look. So I think this one, you're double. Yeah, sorry. Go ahead.
No, I was saying that this kind of thing is like a sort of prior, but that depends on the point where you're looking at. So maybe
but that's
this is what you were saying.
Yeah. So you take that as a hyperparameter, which is the mean. For every weight now has a distribution, and it has a mean.
Yes.
So the outer W is the mean.
Yeah.
The inner one is the actual distribution. The thing with the gamma in front is your prior, and the thing in the first term is the likelihood. And then if you do your variational bound, then the exponents disappear, and you basically get your variational formulation of. Yeah, so I think you'll get back to basically variational base, but then with a soft weight sharing prior that you can update on the outer loop.
Yeah, essentially, I think so, yes.
I also want to mention there's very nice relationship with elastic averaging as well. So
That I'm sorry I didn't mention that, but I should have. This replicated SGD is very, very much related to elastic averaging. Elastic averaging, yeah, absolutely. They were derived from for different reasons, but they end up being very similar. It's not.
Okay, there is last question. There is last question in the chat, and by Leonardo. Leonardo, do you want to step in? If not, he asks, would it make a difference to compare replicated stochastic gradient descent to an ensemble of Y baseline nets with or without interactions, instead of comparing it to one baseline trained on Y and X? Y times.
I should. Yeah, I mean, in a sense, it does make sense, but I should point out this, that even if we, in replicated SGD, even if we use Y different networks, so 3, for example, we always use one network as a classifier. So we don't use an ensemble. So this is not an ensemble classification. This is the one single classifier, which is the mean of 3 replicas which are learning. And by the way, which we also tend to make collapse at the end because of the proper process that is here. So that I was showing here. So when we start with small gamma and increase it further, and in order to get the middle of a wide region. So if we were to compare to, let's say here, let's say that we had the baseline and we had 3 different baselines, all initialized randomly and independently, ran each of those running for 1/3 of the epochs, then you get 3 answers. And what do you do then? You can do
you take the majority.
You can take the majority, yes, but then it means that for testing purposes, then you need 3 classifiers. Whereas at the end of this process here, we end up with 1 classifier and we can throw away the replicas. That's what I'm saying. So the classifier still lives in the same space of a single W as the baseline here. Whereas In the other case, you would have a replicated space even for classification. See what I mean?
I see what you mean. I hope also it answers
Yeah.
to Leonardo. Okay, with that, because we are yes, it does. Because we are out of the time of the discussion time, so let's move the other questions that would potentially be there to the offline discussion. And thank you again, Carlo, and also Ton and Manfred,
Thank you.
the other speakers of this session.